Welcome to Chapter 5.1, Midsegment Theorem and Coordinate Proof. So in Chapter 5, we are going to be looking at all sorts of different relationships found within triangles. So last chapter was all about congruent triangles and corresponding parts of congruent triangles. Now this chapter is just going deeper into triangles and relationships we see and special properties. So midsegment theorem and coordinate proof. We're going to begin with the idea of a midsegment. And a midsegment of a triangle is a segment that connects the midpoints of two sides of the triangle. Every triangle has three midsegments. So if we are looking at side AB on this triangle, M is the midpoint, meaning the distance from A to M is equal or congruent to the distance from B to M. So M is exactly midway between A and B. P is the midpoint of BC. So BP and PC are equal or congruent to each other. So then the segment MP that connects these two midpoints is a midsegment. N is the midpoint of side AC, meaning AN is congruent to NC. So then MN would be a midsegment and PN would also be a midsegment. So now that we know what midsegments are, we're going to look at the midsegment theorem. And the midsegment theorem says the segment connecting the midpoints of two sides of a triangle is parallel to the third side and is half as long as that side. So in this case, if DE was my midsegment, DE is parallel to the third side that it doesn't connect. So DE would be parallel to side AC, and DE is half the measure of AC. So if AC was 20, DE would be 10. So now let's look at that midsegment theorem in a couple scenarios. First one, example one, is dealing with construction. It says triangles are used for strength in roof trusses. In the diagram, UV and VW are midsegments of triangle RST. Find the distance of U to V and the distance from R to S. So what I want to look at is first, I'm looking at the big triangle RST. So R to S to T, this big triangle here. Then I'm told UV is a midsegment, so we want to find UV. UV is right here connecting side SR and ST. So that tells me UV is parallel to side RT and half of its measure. So if RT was 90 inches, half of the 90 inches gives me UV, which is 45 inches. Then in part 2 of this problem, we're looking at VW. VW is right here, and VW was 57 inches. They want us to find the measure of side RS. So if VW is a midsegment and it's 57 inches, it's parallel to side RS, and it's half of RS's measure. So if I take 2 multiplied by the length of VW, I get the answer for RS. So 2 times 57 equals 114 inches for side RS. In example 2, we're looking at a kaleidoscope image. If it's hard for you to see on the black and white here, there is a colored image in your book. But what they told us is segment AE is congruent to BE. So AE here is congruent to BE here, meaning E is the midpoint of side AB. And they told us AD is congruent to CD. So AD here, congruent to CD, meaning D is the midpoint of side AC. So AE is congruent to BE, and AD is congruent to CE, so we know E is a midpoint of AB, and D is the midpoint of AC by definition. They want us to show that side CB is parallel to side DE. Well, DE then, by definition, because it connects two midpoints, DE is the midsegment of triangle ABC, the bigger triangle here. And if DE is that midsegment, by the midsegment theorem, that tells me DE is parallel to CB. And then we get into the second part of our lesson title today, the idea of coordinate proofs. And a coordinate proof involves placing figures on a coordinate plane, so plotting or graphing them. And then when you use variables to represent the coordinates of a figure in a coordinate proof, the results are true for all figures of that type. So instead of calling points like 0, 1 or 5, 3, we're going to be using variables as part of the locations. So these coordinate proofs, by using variables, are showing us rules that are true for all figures of that type. So the first thing they want us to do, place a figure in a coordinate plane in a way that it's convenient for finding side lengths. Assign coordinates to each vertex. So what makes it easy to find a side length of a rectangle would to make sure your 4 points are on whole numbers or points where the X and Y values cross on your grid. So I don't want to put it midway in between two lines. And if possible, you always want to have a vertex at 0, 0 or the origin. So I could have drawn this rectangle a few ways, but I drew mine just like this. Then, instead of giving numbers other than the 0, I'm using L for the length and W for the width. So if I have a point at 0, 0, this point is at 0, W. We don't know W, we haven't assigned it. We're just saying it's not changing where we are at all. Horizontally, our height is just the change in the width of the triangle. So if this is 0, W, going this way, the length would be the letter L. So this point would be L, 0, because I went over L and didn't go up or down at all. Then the fourth vertex, I went the length of L over and W up. So that point would be L, W. Now for the scalene triangle. We want 3 sides that are going to possibly be different lengths. And we want to draw the triangle so that we have easy to read points or vertexes. So I made my first point at 0, 0. Then you could go a random distance over and up. And we'll just call that point X and Y. Over X, up Y. And then the final point would be over Z, 0 in this case, making it easy, because we know the distance of Z is going to be different than Y, which is different than X. Now, the reason that we want to lay them out this way is to make our coordinate proofs as easy as possible when it comes to the midpoint formula or the distance formula. So again, refresher on the midpoint formula, which we did before, but a midpoint formula always has that capital letter M. So it's M equals, and on this one, on top, you would have your two different x values, so x2 plus x1, and that gets divided by 2. And then the other part of our midpoint formula would be y2, so one of our y coordinates, plus the other y value, so y2 plus y1, all divided by 2. And then that goes in parentheses. So it's your x2 plus x1 divided by 2, comma y2 plus y1 divided by 2. That's midpoint. For distance formula, let's change our color here. Distance formula, the whole thing is in the square root again. So our whole distance formula goes under the square root. And this one again is x2 minus x1 in parentheses squared. So that goes in parentheses squared. And then it's plus y2 minus y1 in parentheses. And that whole thing is also squared. So just a refresher on midpoint formula and distance formula. We've used them a couple times already this year. So for the midpoint formula, first they want us to place an isosceles right triangle in the coordinate plane, find the length of the hypotenuse and the coordinates of its midpoint. So if I'm going to be using a right triangle, I want it to be starting at 0, 0. So point A was at 0, 0. Then I know because it's isosceles, two sides have to be the same length. So however high up I went for B, I want to go the same distance over for C. So in this case, 1, 2, 3, 4. I went up 4, but I'm not going to use a 4. I'm going to name that point over 0 up x. And then I'm going to go the same distance to the right to get point C. So that would be x, comma 0. So to find the midpoint of that side, so the rule for the midpoint of that side would be using our point B and C. So we're looking at B and C. Here's our 2 points. So using the midpoint formula, it'd be 0 plus x divided by 2, and then the y values x plus 0 divided by 2. Both of those give us x divided by 2, comma x divided by 2. So that midpoint would be whatever the value of x is divided by 2, comma value of x divided by 2 to find this point. The distance formula for BC, because they also want us to find the length of the hypotenuse. So midpoint formula found me the coordinates of the midpoint of that side. The length of the side, the hypotenuse, which is BC, we're using the distance formula. So that would be change in x, so x minus 0 squared, plus change in y, 0 minus x squared. So we end up with x squared plus a negative x squared. Well, x squared is just x squared. Negative x times negative x is a positive x squared. So that answer would give us 2x squared within the square root. And this answer is also equivalent, going back to the algebra days. We can factor out the x squared that gets square rooted, and that's just x square roots of 2, because we can't simplify the square root of 2. I would take this answer or this answer for the length. So for the midpoint, you use the midpoint formula. For the length, you use the distance formula. Then we get down to our final example for today. Example 5 asks you to write a coordinate proof of the midsegment theorem for one midsegment. So our coordinate proof of this midsegment theorem for any one midsegment. So what I'm thinking is the given info is that DE here is a midsegment of triangle OBC. We're trying to prove that DE is parallel to OC and that DE is 1/2 the distance of OC. So we're trying to prove the two parts of the midsegment theorem. So first thing, we need to find the coordinates of D and E. So the coordinate for D, we're going to use the midpoint of O and B. So 2Q plus 0 divided by 2, and 2R plus 0 divided by 2. So our midsegment would simply be 2Q divided by 2, 2R divided by 2, which is Q comma R. So point D would actually be at the point Q comma R. Then we're going to do the same thing with E. E is the midpoint of BC, so we need to figure out E's coordinates. So the x values added, 2Q plus 2P divided by 2, and then the y values added, 2R plus 0 divided by 2. That gives us for our x value, Q plus P, and for our y value, R. So that would be the coordinates for E. Now we need to prove the two lines are parallel. So the y coordinates of D and E are the same, R and R. So that tells me the slope of side DE is 0, change in y over change in x. Then the y coordinates of 0 and C are both 0. So that tells me that the slope of OC is also 0. So line DE and line OC both have slopes of 0. That proves they are parallel. Same slope, meaning they're parallel. Now we're on to the last part of saying or proving DE is half the measure of OC. In this case, we're going back to use what's known as the ruler postulate, where it's saying, in this case, if I'm using point or side DE to find the measure of DE, whoa, that just went funky. Apologies there. Back to our notes. If I'm finding DE, then I'm going to look at point D and point E. So I'm going to use QR and Q plus P comma R. So the distance there would be Q plus P in parentheses minus Q. So our X value, Q plus P minus the Q, to find that distance there, which would simply be P, because it's in the absolute value. So how far did it change here to here? This was at Q plus P, or this was at Q plus P. This was at just Q, so it changed a distance of P. Then for OC on bottom, 2P minus 0 and the absolute value of that. 2P minus 0 is simply 2P. 2P is twice the distance of P, so we have proven the midsegment theorem. Now going back though to the main idea of today's lesson, the idea of coordinate proofs is using variables to represent values on a grid to show rules that are true for all types of those figures. And then back to the idea of a midsegment and a midsegment theorem, meaning if DE is that midsegment, it's parallel to AC and half of its measure.